Hi class, in this lecture I want to do a quick introduction to rational functions for you. So what exactly is a rational function? So a rational function is a function of the form, we'll call it r of x is equal to p of x divided by q of x. And this is where p and q are polynomials. So we assume that p of x and q of x, right as it's listed, have no common factor. Okay, so nothing cancels out. So even though rational functions are constructed from polynomials, their graphs look quite different from the graphs of polynomial functions. Okay, so let's talk about rational functions and what we call asymptotes. So the domain of a rational function consists of all real numbers x, except for those for which make the denominator 0. The reason you can't do that, right, is you can never have it divide by 0. So when graphing a rational function, we must pay special attention to the behavior of the graph near those x values. Okay, so where the value of x would make it divide by 0. So we're going to begin by graphing a very simple rational function. So we're going to graph the rational function. The easiest one is this one. F of x is equal to 1 over x. And what I want to do is I want to state the domain and range of this function here. Okay, so the function f is not defined for x is equal to 0. Okay, the reason you can't do that is because then you'd have 1 divided by 0. So the following table shows that when x is close to 0, okay, on each side, okay, the value of the absolute value of f of x is large, and the closer x gets to 0, the larger this gets. Okay, so like if you were to take these numbers here, negative 0.1, negative 0.01, negative 0.00001, and plug it into your function, these are the values you would get. So what it looks like is, as you're approaching 0 from below, so on the negative side, it looks like your function is going down to negative infinity. It's decreasing without bound. The flip side is, as you are approaching 0 from the right, or from the positive numbers, it looks like your function is blowing up. It's getting larger and larger and larger and approaching positive infinity. Okay, so we describe this behavior in words and symbols as follows. Okay, the table shows that as x approaches 0s from the left, the values of y decrease without bound. Okay, so in symbols it's this. F of x goes to negative infinity as x goes to 0 from the left. So y approaches negative infinity as x approaches 0 from the left. All right, the second table shows the reverse of this, right? So the second table shows that x approaches 0 from the right. The values of f of x increase without bound, so they go to positive infinity. So this is what this looks like in symbols, the flip side of what I was just saying. Okay, so the next two tables show how f of x changes as the absolute value of x becomes large, right? So as x goes large, so to negative 10, negative 100, negative 1000, it looks like when you plug that into 1 over x, f of x gets really small, okay, on the negative side. It gets really close to 0, but from below. The flip side is true with positive numbers, okay? You're going to approach 0 from above. So the tables show that the absolute value of x becomes large. The values of f of x get closer and closer and closer to 0. Okay, so we describe the situation as the following. F of x goes to 0 as x goes to negative infinity, and f of x goes to 0 as x goes to positive infinity. Okay, using this information in these tables and plotting a few additional points, we obtain the graph that you're seeing here. So as x gets close to 0 from above, the graph is going to shoot up to positive infinity. As x gets close to 0 from below, the graph is going to shoot down to negative infinity. Notice it never crosses the y-axis. And it's the same deal on this side. As x gets large, all right, as x increases without bound, the function is going to get closer and closer to 0, but never crosses the x-axis. And the same thing on this side. As x decreases without bound, okay, the function gets closer and closer to 0 from below, but again, never crosses that x-axis. Okay, so what we see here is the function is defined for all values of x other than 0. So the domain of this function is x such that x is not equal to 0. And also from the graph we see the range is all possible values except 0. This graph can never be 0 because it never crosses the x-axis. So the range is y such that all y's are not equal to 0. Okay, this line, x equal to 0, the one it never crosses, okay, the y-axis there is a vertical asymptote of the graph, and the line y is equal to 0, or the x-axis, is what we call the horizontal asymptote. All right, so informally speaking, an asymptote of a function is a line to which the graph of the function gets closer and closer and closer as one travels along that line, but it never crosses and never touches the line. It gets super, super close to it. All right, so here are the definitions of these verticals and horizontal asymptotes. So a line x is equal to a is a vertical asymptote of the function if y approaches positive or negative infinity as x approaches a from the right or left. So these vertical asymptotes, this function is going to bump up against it or bump down against it. The line y equal b is a horizontal asymptote of this function if y approaches b as x approaches plus or minus infinity. So like as you can see here, as x goes to infinity, it approaches the value b. And here as x goes to negative infinity, you see the graph is going to bottom out and approach this value b. All right, so let's talk now real quick about transformations of this function. So a rational function of this form now, r of x is equal to ax plus b divided by cx plus b, can be graphed by shifting, stretching, and or reflecting the graph of 1 over x. All right, so let's graph these two functions here and state the domain and range of each. Okay, so for the first one here, I have r of x is equal to 2 divided by x minus 3. And the second one, s of x, I have 3x plus 5 divided by x plus 2. Okay, so for this first one here, I'm going to let f of x be 1 over x. So we can express this function r in terms of f as the following here. Factor out the 2. Well, what's now looking at this, what's the difference between this and this x? Well, I'm not plugging in x, but I'm plugging in x minus 3 into the function. So from this, we see that the graph of r is obtained from the graph of f by shifting it 3 units to the right, because whenever you're inside the function here, it works the opposite way you would think, and then stretching vertically by a factor of 2. Okay, so thus r has a vertical asymptote then because it's getting moved to the right 3 spaces at x is equal to 3, and the horizontal asymptote stays the same. So you can see here what this graph is going to look like. Okay, it has its vertical asymptote at x is equal to 3 now, and it's still going to bump up against it from the right and go down to 0 this way, and then bump down against it from when you come from below, and so on. So the function r is defined for all x other than 3, so the domain is x such that x is not equal to 3, and then again from the graph here we can still see the range is y such that y is not equal to 0. Okay, this one here, the next one, you're going to take this going back, and you're going to do long division to clean this up a little bit. So doing long division, we can see that the function is now the following. It ends up being 3 minus 1 over x plus 2. Now we can express this in terms of f as the following. Okay, we're going to rearrange the terms. This is going to be plus 3 at the end of my function. I'm plugging in x plus 2, and then I'm negating it. So from this, we see that the graph of s is obtained from the graph of f by shifting 2 units to the left, right, and then reflecting in the x-axis and shifting upwards 3 units. Okay, so when we do all that, s has a vertical asymptote at x is equal to negative 2 and horizontal asymptote at y is equal to 3. So you can see the graph here. All right, so now you got to think about what the domain and range of this is, right? So the domain is all x other than negative 2 because I can't have it divide by 0. And the range is all values except for 3. So you can see the domain is all values but the vertical asymptote, and the range is all values but the horizontal asymptote here. Okay. Just go a little bit more and talk about asymptotes of rational functions here. Okay. How do we find asymptotes? So to graph more complex problems, we're going to need to take a closer look at the behavior of rational functions near its vertical and horizontal asymptotes. In general, if r of x is equal to p of x over q of x, and the degrees of p and q are the same, say they're both n, like 5, okay? The degrees of the polynomials, or 2, whatever. Then dividing both the numerator and denominator by x over n shows that the horizontal asymptote is always the following. Okay, the horizontal asymptote is y is equal to the leading coefficient of p divided by the leading coefficient of q, as long as the degrees are the same. All right, so the following block summarizes the procedure for finding asymptotes. Okay, so we have 2 rational functions, okay? We have an, xn, and then the rest of it divided by bm x to the m. What you're really interested in here are the degrees of each, n and m, and the leading coefficients, an and bm. All right. If n is less than m, so like if n is 3 and m is 5, then R has a horizontal asymptote at y is equal to 0, the x-axis. If the two are equal, like this is 3 and 3, then the horizontal asymptote is the ratio of the leading coefficients, an divided by bm. And if n is greater than m, like this is 5 and this is 4, there's no horizontal asymptote at all. All right, so let's do an example. Let's find the vertical and horizontal asymptotes of this. Okay? So first off, let's do the vertical asymptotes. You're going to factor the denominator, okay? Then you're going to see that it's going to factor into 2x minus 1 times x plus 2. You can never have a divide by 0. So one factor here, when you set this equal to 0, excuse me, when you set this equal to 0, you're going to get x is equal to 1/2. When you set this equal to 0, you get x is equal to minus 2. So therefore, there are vertical lines at x is equal to 1/2 and x is equal to minus 2. The horizontal asymptote here, when you look, the degrees of the numerator and denominator are the same. Okay, they're going back. They're both 2. So the horizontal asymptote is the ratio of the leading coefficients. Okay, so the horizontal asymptote is just this line y is equal to 3/2. All right, I hope that helped as a quick introduction to rational expressions.